Hello everyone and welcome. My name is Tom Janssens and today I would like to present my thesis topic of semi-analytical modeling of variable stiffness laminates with discontinuities. Composite materials are being used more and more as they can decrease the weight of a structure, they can improve its performance and ideally do both simultaneously. However, they come at an increased cost of design and analysis tools required. Take for instance the isotropic plate with a cutout. We know the stresses flow around the cutout, yielding stress concentrations near the cutout edge. But how do these stress concentrations change if we have, for instance, a variable stiffness laminate with the fiber pattern shown on the screen? This is a prime example of the complexity of design and analysis where usually large finite element models are required. This is what has driven Saulo and myself to ask the question if a semi-analytical model can be developed to determine the mechanical behavior of variable stiffness laminates with discontinuities. To create this model, I will show you what I've done in terms of my methodology or my tools. I will show you some pre-buckling cases that I have analyzed, some buckling cases before finishing with some recommendations and conclusions. The model is based on energy methods using the Rayleigh-Ritz method, where the total energy in a structure is determined and minimized with respect to input shape functions. However, if we look at a plate with a cutout, there is an increased local effect surrounding the cutout. So if we take a look at the deflection along the line, we can see there's an increased local effect next to the cutout edges with respect to the global effect. To overcome this problem, I have added enriching functions, which are additional sets of shape functions which can take into account this local behavior better. So rather than having a single set of functions to determine the behavior, I can add an additional set of functions, and I can even add a third set of functions in a different coordinate system, such as polar coordinates shown on the screen. To overcome the difficulties of determining the energy of this variable stiffness laminate with multiple sets of shape functions, the Gauss-Legendre Quadrature is used for numerical integration. The evaluation points obtained from this method can also be transformed into circular points, which allows me to determine the energy across my laminate with a rectangular outer domain with a circular cutout. As an overview, with the plate properties such as dimensions or stiffness variations, the shape functions including the enrichment functions and the integration points as input, the energies can be obtained for the outer domain and the center domain. These energies can be subtracted to give the energy for the plate or laminate with a discontinuity and determine the outputs in terms of stresses or displacements. So first, let's take a look at the pre-buckling or in-plane cases. For this case, the laminate is loaded by a uniform compressive displacement where the transverse edges are free to deform, and the Airy stress function is used to reduce the number of unknowns as only one function needs to be approximated by the shape functions. So with the stress-based approach, the ny and nxy along the horizontal edge will be 0. The nxy along the vertical edge will be 0, but nx will have a distribution due to the stiffness variations and the uniform applied displacement. So we need an additional approximation for nx at the edges. Along the cutout edge, no suitable shape functions were found to comply with the boundary conditions. Rather, a residual thickness approach has been taken, where the model takes the laminate to be continuous, but the thickness of the cutout region is reduced by so much that it deems it cannot carry any load. So the load must be distributed around this cutout region. 4 sets of shape functions have been chosen to approximate the Airy stress. The first relates to this edge distribution of nx. The second is a homogeneous solution in natural coordinates, and 2 sets of enriching functions have been added in polar coordinates. 4 sets of results will be shown. 2 related to a composite plate, 1 related to an isotropic plate with a cutout, and finally 1 related to a variable stiffness laminate with a cutout. Starting with a composite plate with a square insert of higher stiffness than the surrounding laminate, the result shown is the axial load nx obtained from the semi-analytical model and finite element analysis. This case is from a reference paper and served as a means of verification to recreate previously published results. As a continuation of the previous work, the section is transformed into the circular domain and the shape functions presented in this work are used. Again, the results are compared to those from finite element analysis and agree very well. Then an isotropic plate with a cutout is analyzed. Here the residual thickness is used and the model provides good results for the nx when compared to finite element results. The same is true for the ny loads and also for the nxy loads. When looking at several sections of the plate and comparing the results, it provides some more insight. So here we take a look at the approximation provided due to the applied displacement along the vertical edge. There are some differences, but overall there's a good agreement. If we take a look along the half width of the plate, moving towards the cutout, again we see a good agreement minus a small difference at the cutout edge. More interesting thing happens when we take a look at the loads along the half length of the plate moving towards the cutout edge. There is an increase in oscillations in the loading provided by the model, and this is believed to be a consequence of the residual thickness. The model predicts the loads inside the cutout region to be zero, which is what the residual thickness approach is supposed to do. Therefore, the loads must approach zero within the cutout region, yielding this jump in loading close to the stress concentration at the cutout edge. We did not see this in the previous slide, as the NX load in that situation already goes to zero at that point in the plate. The next case is that of the variable stiffness laminate with the shown fiber path. The semi-analytical model provides the following results, and immediately we can see that the higher loads have been redistributed along the horizontal edges with the higher axial stiffness. When comparing to finite element results, the symmetry is used, and immediately we can see a good agreement between the results, but similar to the previous case, we shall look a bit more into detail. The results for the actual loads along the vertical edge are seen to be matched very well. When moving along the half width of the laminate, again, the results match very nicely. And when we look along the half length of the plate, we can see the oscillations that were there in the case of an isotropic plate are no longer there. And this is due to the variable stiffness. The stress concentration is severely reduced, and the jump needed to get the zero loads inside the cutout is very small. So with these pre-buckling results, the analysis is moved on to buckling. The buckling model uses the previous results as input and uses a displacement-based approach for the buckling behavior. So the geometric boundary conditions are simply supported edges and the cutout edges are free, which means there is no need to use a residual thickness approach for the buckling analysis. 3 sets of shape functions are used, 1 set for the global behavior and 2 sets of enriching functions for the local behavior. First, the results for an isotropic plate with a cutout are obtained and compared to those from finite element results. The eigenvalues shown are in terms of the applied loading and thus represent a uniform applied displacement. As can be seen from the table, the results again show good agreement, and as the buckling formulation takes into account the in-plane loads in an average sense, the oscillations that we saw in the in-plane loads cause no large differences in the buckling results. The buckling modes obtained from both the semi-analytical model and the finite element model also show good agreement for the first eigenmode, and similarly also for the second eigenmode. For the variable stiffness laminate, the comparison is made between the laminate with and without a cutout. In the case of the eigenvalues can be seen to be very close to one another, indicating that the laminate maintains much of its buckling performance even when it has a cutout. This is again seen in the buckling modes, where the buckling modes hardly change due to the presence of the cutout. Again for the second eigenmode. So finally, some recommendations. First of all, the displacement-based approach has the great advantage of not needing the boundary conditions along the free edges of cutouts. It will be an improvement to the model to include displacement-based formulations for the pre-buckling analysis. Some more work could be done regarding different shapes and locations of cutouts or discontinuities, where in this work only central circular cutouts have been considered. The work so far does not include any failure analysis and does not include any optimization. And finally, it will be worthwhile to explore and expand the possibilities of this model, for instance, to use it in cases of filled holes or joint analyses. So in conclusion, can a semi-analytical model be developed? Well, enriching functions provide a solution for local behavior, and numerical integration schemes can be used to make life a lot easier. Results show good agreement with results from finite element methods, and the model is easy to use with varying inputs, for instance with stiffness variations, fiber paths, etc. So yes, such a model can be developed. And I would like to thank you very much for your attention.